Hi, Assalamualaikum warahmatullahi wabarakatuh. Allow me to introduce myself. I'm Fidiyarsi Matari with the student ID 1906356241 from the class Numerical Method 1. So today I'll be explaining about solving systems of simultaneous linear equations using OpenModelica by solving the previous Truss problem given by our assistant Bang Edo. So before moving on to the problem, I'll be explaining first about linear algebra. What is linear algebra? Basically, it is a system of equations that can be represented as a product of matrices or as an augmented matrix. It is usually in the form of AX equals B. A particularly useful representation of the equations for computational purposes is the augmented coefficient matrix obtained by adjoining the constant vector B to the coefficient matrix A in the following fashion. And as for the examples, here are the examples for the product matrices above and the augmented matrices. As for the methods, there are two methods, which is the direct method, which calculates the solution after performing a finite series of computational operations. It is also called direct counting. It is best for solving small filled matrices. The examples are Gauss elimination method and Gauss Jordan method. As for indirect method, it approaches the solution by improving an initial guess until the error is negligible. It is also called iterative approximation. It is best for solving large sparse matrices. And as for the examples, there are Jacob method and Gauss-Seidel method. Now let's move on to the problem. I'll be explaining three things: the question, how to solve it, and the result. So this is the question. This is question number 4. The members of the truss shown in the accompanying figure have a cross-sectional area of 10 centimeters square and are made of steel with a modulus of elasticity 200 GPa. Using hand calculations, determine the deflection of each joint, the stress in each member, and the reaction forces. Verify your results. So this is the question. And as you can see, there are two fixed joints in node 1 and 3. And there are the applied loads of 4 kN and 4 kN. So from the question, we can know the properties that we need. First of all, the area, which is 0.001 meters square, the modulus of elasticity, and the loads, which are projected towards the x-axis and the y-axis. It is in point 2 and 4. And as for the trusses, there are 5 trusses, and each truss has 2 nodes. So we define the trusses. For truss 1, it is 1, 2, 2, 2, 3, 3, 2, 4, etc. Now let's solve the problem. So our first step is to input the parameter. This is our main model or our main code file, which is trusses_number4.mo. And here we have to input the parameter or the properties that we have, such as the area, modulus of elasticity, and as well as the applied loads. Not to forget the boundary conditions, which is located at node 1 and 3, which are fixed joints. Moving on to our second step, we have to assume a solution that approximates the behavior of an element. So here we'll be using the formula K equals AE over L, and here we input it for all 5 trusses. So for our third step, we have to solve stiffness matrices for each element. This is the formula that we'll be using, and we input it to our call function called matrix_stiffness.mo, and later on we will be using this. Our fourth step is to convert the stiffness matrices into global format. And this is another call function called LCL_global.mo, which we will also be using later on. As for our fifth step, the global stiffness matrix is obtained by adding together the individual element stiffness global format matrices. So we combine the call function of matrix_stiffness.mo and LCL_global.mo, and we count for each G, and we add it together to get the global stiffness matrix. This is the main model of trusses_number4.mo. And for our sixth step, we apply the boundary conditions and loads. So we know these boundary conditions where in node 1 and 3, it is a fixed joint. So there is no displacement. So u1x equals 0 and u1y equals 0 and u3x equals 0 and u3y equals 0. So we input it here, the boundary conditions, in the main model of trusses_number4. And in the seventh step, this is where we solve for the node displacement, and we will be using the direct method of using Gauss Jordan. So here we create a call function for the Gauss Jordan, which is called trusses_Gauss Jordan.mo. And this is in the main model of stresses underscore number 4.mo, where we use the call function and we solve for the displacement. And in our 8th step, we solve for the reaction forces. So again, this is the call function for solving the reaction forces with that formula. And here we solve for the reaction force in the main model of stresses underscore number 4. And we get the result. So this is the result displacement graph, which looks like this, which is the displacement towards the nodes. So 0 is node 1x, 1 is 1y, 2 is 2x, 3 is 2y, etc. And we also get the number or the value of the displacement, which is defined by Sol. And this is the result for our reaction forces graph here, as well as the value for the R, which the value for the reaction forces, which are defined by R. And that is all for my presentation. Thank you for paying attention. Wassalamualaikum warahmatullahi wabarakatuh. Inshallah, this presentation could prove to be beneficial for us all in the present and hopefully in the future as well. Thank you.